So today we're going to look at two different kinds of nonparametric tests. The first we're going to look at is a Mann-Whitney-U test, and then afterwards we're going to look at a Kruskal-Wallis test. So Mann-Whitney-U is the nonparametric equivalent of a t-test. That's up here. And then the Kruskal-Wallis is the equivalent of a one-way ANOVA. And contrast testing in nonparametrics is done with a Dunnett's test. So how do you know whether or not to use nonparametrics versus parametrics? The answer to that is whether or not you violated your assumptions. If you have violated your assumptions, then really what you should be doing is using nonparametric analyses. So let's load up a dataset. We're going to use the ADD dataset from much earlier on in the course. And we're going to look at IQ and dropout. So the participant's IQ score and whether or not they dropped out of high school. So let's run the t-test and our equal variance. And let's just see what's going on here. So I've violated the assumption of equal variance right off the bat, and I also have an unbalanced design. So I can see here I have 78 people who didn't drop out, 10 people who did, and if I look at their standard deviations, they are drastically different. So without even looking at normality, I'm already going, I shouldn't be running a t-test on this. They're just wildly different. If we look at the t-test statistics, it does say that there is a difference between my means, suggesting that those who don't drop out of high school have a higher IQ. That kind of makes sense, but nevertheless, let's just be a little bit more careful and rerun this as a nonparametric analysis. So here we're going to use the command rank sum. So for the t-test, we're going to be taking that ranked sum approach that I showed you earlier, where what we're doing is we're ranking each of our scores and then summing them up. So rank sum, IQ, because that's our DV here, and then by dropout. Okay, so what we can see here is we have 78 observations for not dropout, 10 for those who did drop out. The rank sum for not dropouts is 3,699, and the rank sum for high school dropouts is 217. The expected is 3,471 for not dropouts and 445 for dropouts. So what is the expected column actually saying? This expected column, the whole point of it is effectively just to say, if my rank sums were equal, these are the rank sums that I would get. So if within the realm of error, the scores were equally distributed, so there was no sort of banking on the left or right hand side of the distribution, IQ scores didn't differ depending on whether or not you dropped out, we would see an approximate rank sum of 3,471 for those who didn't drop out, and a rank sum of 445 for those who did. So this then leads on to the question, if these rank sums represent no difference in IQ, why aren't their rank sums equal? And the answer to that is quite simply that there's different numbers of observations in each group. So there are 78 ranks being contributed to this rank sum, yet there's only 10 here. So what this means is, because there are fewer ranks going into this sum, for those who did drop out, it's always going to have a lower rank sum than when I add up the 78 for those who didn't drop out. So this expected rank sum gives me an idea of, well, if all things were equal, what would be my rank sums, given that we don't have equal sample size. And what we can see is that the rank sums for those who didn't drop out is higher than expected, whereas those who did drop out, they have a rank sum lower than expected. And this is telling me then that those who didn't drop out have the higher IQ because the rank sum is higher than it's expected, whereas those who didn't drop out have a lower IQ because they're lower than they're expected. Down here we have a measure of variation along with an adjustment for ties. Adjustment for ties just means if you have two scores that are the same value, rather than considering them separate ranks, you consider them to be the same rank. And so that's going to reduce your variation in your rank sums just a little bit, because you're going to reduce the number of ranks that you're using. And that's the most appropriate approach, is to adjust for these ties. That leaves us with a final variation of 5,779 units. You don't really need to know what's happening here, except for the fact that this adjustment for ties is accounting for the fact that you've got two values that are the same and you're making them have the same rank. But we can use the variation along with the ranks to then calculate z-scores. Particularly a z-score representing the null hypothesis that the IQ between our two groups is equal. So that's just your standard t-test null hypothesis, that for a t-test it would be the mean IQ rate is the same for both groups. Here we're saying the rank sums would be the same. The z-score we get is 2.999, which is certainly higher than our usual cutoff of 1.96 and a bit. And we can see this reflected in the fact that our p-value is less than 0.05. So this is telling us that there is a significant difference in IQ scores, or in the ranks of IQ scores, between those who did and didn't drop out. This, however, then leads on to the next question, well, who does have the higher? How do we know? And the answer to that is, well, actually, you can't use nonparametric analyses to make conclusions about actual magnitude. You can't go now and say, well, the mean for not dropouts is this, whereas the mean for dropouts was this. Because if you could do that, you would have been running your t-test. You could report the median if you wanted, but technically speaking, rank sum isn't exactly medians. So that's not really what you've compared. So it sort of leaves you going, what do I do with this information? They're different. I know the order of the difference, but I can't talk about the magnitude. And this is one of the major limitations of running a Mann-Whitney t-test or a nonparametric test of almost any flavor. You can talk about the order of effects, but you can't really talk about the magnitude that comes with that. And so it becomes quite limiting. It's sort of like, well, then what do we do with this information? Where do you take it? Interestingly, though, if you look at the t-test, you make the same conclusion based off significance. Like, the p-values are actually pretty close. And so what this might actually suggest is, despite the fact that we don't have equal variance, it actually isn't really impacting the integrity of the t-test too much. So there are two schools of camp here. One says if you have violations of assumptions, you shouldn't go anywhere near the parametric test. Others would argue, well, actually, if the results reflect each other and they seem to be the same and you draw the same conclusion, why sell yourself short of the t-test? It gives you more information, it gives you something you can actually use. There's more pros than there are to cons. Why not just go ahead with it anyway? So I guess that's just a little bit of a food for thought as to what do you do when these are both having the same results. But I did want to bring up with you the issue of taking these results and actually making something meaningful out of them. Something that you might have noticed at this point is our Mann-Whitney U-test is also labeled as a Wilcoxon rank sum. There are lots of instances in statistics where 2 or 3 people have come up with the exact same thing at approximately the exact same time without knowing it. And Mann-Whitney U and the Wilcoxon rank sum is a perfect example of this, where 2 people have come up with the exact same test without being aware of it, and both of them now exist. Another example of this is our p-values. They are actually the result of 3 different researchers. And you'll see more of these cases where 2 or 3 people have come up with the same thing throughout the course, throughout future courses in statistics. So that gives us a bit of an insight about t-tests, and I guess the takeaway is that really it's the same thing, it's just a different way of defining the middle point. Do we use the mean? Do we use rank sum?